Historically, enterprise applications were built to stand entirely on their own. We designed them as tightly coupled, monolithic systems, perfectly optimized for one specific task, but completely isolated from the rest of the business. This approach, known as vertical integration, focuses on deepening the connections within a single application stack. If you look at a specialized hospital billing system, the presentation, business logic, and data layers are heavily intertwined to ensure high performance for that one specific function. The drawback to this optimization is isolation. When every system is built vertically, the enterprise becomes a landscape of data silos. A highly tuned billing application cannot naturally share patient records with the pharmacy or scheduling systems. Modern business processes demand horizontal integration. Distinct departments, CRM, ERP, HR, need a shared infrastructure for workflows. The engineering instinct is to write custom code connecting every system directly. This works for 3 systems, but with dozens of applications, these unique hard-coded connections grow exponentially. The result is known as spaghetti architecture. It is a brittle, unmaintainable network where updating a single component in one application can break integrations across the entire company. To resolve this complexity, architects rely on an abstraction layer called middleware. True horizontal integration cannot be achieved by hardwiring systems together. It requires an intelligent intermediary to intercept, translate, and route the chaos of enterprise data. To understand how middleware operates, we have to look at where it sits in the enterprise architecture. It occupies a distinct space right between the operating system at the bottom and the business applications at the top. Its core function is to act as the software glue. Instead of applications talking directly to the operating system or the network, they communicate only with the middleware. This creates a strict boundary of abstraction. Middleware handles the underlying mechanics of communication protocols and data routing, keeping those details completely hidden from the applications themselves. By standardizing how these systems interact, you achieve interoperability. A legacy on-premise database can seamlessly exchange records with a modern cloud application. This layer houses specialized components. You have database middleware managing connection strings, application servers hosting enterprise runtimes, and transaction processing monitors ensuring complex financial exchanges execute reliably. While these components are highly effective for managing specific, localized connections, scaling data exchange across an entire enterprise requires a more sophisticated, message-driven approach. By offloading the communication logic to the middleware, applications are no longer burdened with managing direct dependencies. Developers can focus entirely on writing business logic. The engine behind that message-driven approach is message-oriented middleware, which relies on a foundational structure known as a message queue. A source system, the producer, pushes an event packet to a central queue. It uses a fire-and-forget mechanism, instantly moving to its next task. On the other side, a destination system, the consumer, pulls packets at its own processing speed. This achieves true system decoupling. In a traditional synchronous connection, the producer would be locked in a waiting state until the consumer confirmed receipt. Here, they operate completely independently. Consider a server crash. If the consumer goes offline, the producer is unaffected, pushing new data into the queue. The queue provides fault tolerance, safely persisting incoming messages. When the consumer reboots, it simply pulls from the accumulated backlog. No data is lost. The same mechanic provides load leveling. If a sudden spike in front-end traffic generates thousands of immediate requests, the queue buffers the impact, protecting older legacy systems from being overwhelmed. Because of this resilience, asynchronous queues are the ideal mechanism for separating concerns within modern microservice and event-driven architectures. By eliminating the expectation of an immediate reply, asynchronous communication ensures that a localized failure in one department never cascades into a total network outage. As resilient as queues are, they don't independently solve the topological nightmare of spaghetti architecture when dozens of applications need to talk to one another. Rather than wiring applications directly to each other, every interaction flows through the ESB. Inside the bus, the ESB executes data transformations. It intercepts a payload from an older system, translating it into a modern format on the fly. It also handles intelligent routing, dynamically directing messages to the correct destination based on predefined rules. This allows architects to orchestrate complex workflows. A single trigger hits the ESB and is sequentially routed to billing, inventory, and shipping systems in a coordinated process. This model does have limitations. Because a monolithic ESB handles every translation and route, it requires intense management and can quickly become a performance bottleneck or a single point of failure. To address this, modern distributed patterns often shift some of these workloads away from a heavy central bus, distributing the routing and translation duties toward decentralized API gateways and event streaming platforms. Despite this evolution, the ESB remains a crucial backbone for large organizations. It serves as a universal translator, enforcing predictable, standardized flows across the entire network. To connect applications to a middleware hub like an ESB, both sides must first agree on exactly how they will communicate. They need an interface contract. We define these contracts as application programming interfaces, or APIs. An API provides a structured set of rules, allowing one machine to request specific data from another, without needing to understand how that data was generated. When these APIs are exposed over a network, we classify them as web services. Designing these web services forces a direct engineering trade-off. Architects must choose between a strict protocol and a flexible architectural style. For highly standardized, robust integrations, like moving financial data, architects often use SOAP, the Simple Object Access Protocol. It enforces a strict contract, ensuring that every message conforms exactly to a predefined structure. The drawback to SOAP is its rigidity. It relies heavily on XML, making payloads verbose, generating bandwidth overhead, and rendering integrations complex to debug. The alternative is REST, or Representational State Transfer. Rather than a rigid protocol, REST is an architectural style that leverages standard HTTP methods to interact with data. REST is stateless and highly scalable. Instead of bulky XML payloads, it uses lightweight, human-readable JSON, making it incredibly fast to parse. Because of this simplicity, REST has become the default mechanism for exposing external APIs, integrating cloud-based SaaS applications, and linking independent microservices. Selecting the right contract dictates the performance of the entire system. SOAP provides necessary transactional rigidity, while REST offers agile scalability. Applying the wrong interface can easily turn a well-designed middleware deployment into a rigid bottleneck. Enterprise architecture is no longer about building perfectly optimized vertical stacks in isolation. The modern standard is a horizontal enterprise, built on a shared layer of software glue. In this environment, message queues act as the necessary buffer, enabling asynchronous communication so that systems can handle sudden traffic spikes without crashing.
The Enterprise Service Bus operates as the central traffic cop, actively translating payloads and enforcing routing rules so that older, monolithic mainframes can safely talk to modern applications. And REST APIs provide the lightweight, standardized contracts that allow thousands of distinct microservices to connect and scale effortlessly. By mastering these integration patterns, architects can move past the limitations of siloed data. They can construct a modular, horizontal infrastructure that adapts quickly to new technical demands, allowing the entire organization to operate as a single coordinated system.